Okay, let's continue. So after seeing how does the DFS work, and the next part is we want to discuss different types of the edges. Well, of course, we know that if we follow all the red edges on this example, and what we get a tree or multiple trees as a forest, right? So if we only need to keep all the red edges and throw all the remaining edges away, and then we have the tree or the forest. Okay, so those are the tree edges. And then for the tree edges, the next question is, can we have the tree edges and form cycles? Why or why not? So, well, remember when we discuss this part, we say, do we want to take this edge from the 3 to 1? And then we say we don't want to do that. Why? Because we are only doing the depth first search to find the white nodes, right? So this will guarantee that we can always use that algorithm to explore new white nodes. However, we will never go back to a green node or a black node because we have already explored that. So this algorithm will guarantee that we won't go back to an explored node. So this means we won't have cycles if we only keep the tree edges. Okay, so all the red edges are the tree edges. So the next part are black edges. So for the black edges, they are from descendants to the ancestor. However, they are not part of the tree nodes. So for example, like this one. So this is from a descendant to the ancestor, which is the tree root. However, it is not part of the tree edges we are going to keep, right? And the next one, forward edge. So forward edge is the edges from ancestor to descendant, and they are not tree edges either. And well, usually they're from the green node to the black node. And for example, this purple one. So for this purple one, and there is actually a path from the 112 to 27 and then to 56, right? So this is the grandparent, parent, and the child. However, there shouldn't be another path from the grandparent directly to the child. So this path is not part of the tree structure either, and that is a forward edge from the ancestor to the descendant. Okay, and the last one is cross edge. So cross edge are the edges between a tree to another tree, or a subtree to another subtree, or a tree to another subtree of a tree. Okay, so those are all the possible cross edges. Let me give you a few examples. For example, well, let me go back and show you this. So, well, to make the discussion easier, and I have done is I have drawn this graph and showing all the tree structure of all the nodes. So, if I'm only keeping the red edges or the tree edges, and then I can draw this graph of two different trees, right? So, let me come back here. So how about we take a look on this one? That is from 1316 to 811, right? 1316 to 811. And then this is, let me change the pen color. Let me use blue then. Okay, 1316 to 811. What is that? That is from one tree to the subtree. So this is a subtree, right? So from one tree to the subtree of another tree starting from the 112. So that is called a cross edge, and this is not part of the tree structure we want to keep. And let me give you another example. So how about 811 to 56? So 811 to 56. So 811 to 56. And what is that? So that is from a subtree to another subtree. So even though those two subtrees, they belong to the same tree with 112 as the root, however, those two, 811 and the 56, they belong to two different subtrees, and there shouldn't be a cross edge. Okay, so those are two different examples. It can be from one tree to another tree, or it could be from one subtree to another subtree. So those are the examples of the cross edges. Okay, so using the DFS, and then we can introduce the definition of the four different types of the edges. And usually, for most algorithms, we will distinguish the tree edges and the black edges. But usually, people don't emphasize a lot in distinguishing the forward edges and the cross edges. And here is a theorem in our textbook, the theorem 20.10. So if this G, the graph, is undirected, and then the DFS will only produce the tree edges and then the black edges. So this means there won't be forward edges or cross edges if we are doing the DFS on an undirected graph. So let's draw one and see. So if we want to do a DFS using this graph, and then this is the source, and then this is the tree edge, another tree edge. And then how about this one? Can we say this is a forward edge? So for a forward edge, that is from the grandparent directly to the grandson, right? So it seems that this is a forward edge. But if that is a forward edge, this is also a black edge, which is the descendant to the ancestor. So for this one, is this a forward edge? No, because we will take that as a black edge. So, the theorem says, there shouldn't be any forward edge or cross edge available if you're doing this in the DFS in an undirected graph. We want to give a counter example, but we failed because this won't be taken as a forward edge. It will be taken as a black edge. And let's do another one. If we have the source, and then we have the tree edge here, and then two tree edges here and here, and then this one. This will be a cross edge, right? But the theorem says if we are doing the depth first search, and then we won't have cross edge. And can we have this one? Okay, that is a tricky question, and you have to understand how do we do the depth first search. So from the depth first search, we will go this direction. And after that, we want to pick one direction to go deeper, so we go this one. And after that, if there's still another way that we can go deeper, we should go here. Okay, so what does this mean? Well, we are arguing that this C is a cross edge, but we are wrong because this edge, instead of being black, this edge should be red. And for this edge, we argue this can be black, it can be red, but that's wrong. It has to be a black edge. Okay, so this is the argument. The argument doesn't hold because, if we are running a depth first search, and then this edge has to be part of the tree edge, so it won't be a cross edge. And for this one, this is a black edge, and then there's no argument. It's not a cross edge, it's not a forward edge. It has to be a black edge. So this can prove the theorem 20.10 because and saying if we are running the DFS on an undirected graph, we will end up with only tree edges and black edges. Okay, and another definition is for a undirected graph, we call that a cyclic. If a DFS use no black edges. So a cyclic means, well, this graph has no cycles at all. And then, well, it is if and only if a DFS use DFS will say all the edges are the tree edges. There are no black edges. And of course, because we are doing the DFS on an undirected graph, that won't be any cross edges. There won't be any forward edges. And if there's also no back edges, and then this graph is already a tree structure, right? So, well, this means after we running the DFS, we are keeping all the edges as tree edges, and then there's no cycle because we end up with several trees. Okay, so we can modify the algorithm of the DFS to search whether there is a cycle in the graph structure or not. And how can we do that? We can modify the DFS a little bit. So remember, how do we tell if there is a cycle? So when we are visiting a node, and then from this node we can go back to a black node, or if we can go back to a green node. And what is that? So there is a way for us to go back to a node we have already seen, right? So that's the reason that when we go back and then we see a black or we see a gray, and then we can immediately say, okay, I find one cycle. As long as I find one cycle, I don't want to continue this search anymore, and then I will return, I have find a cycle. Okay, so if we are modifying this algorithm to find cycles, then how do we do that? So do we have okay, so let me change the color. So, well, at the very end, and I will do a return, return false, saying there's no cycle here. And if for each of the vertices, if that vertex is already is a white, and then what do we do? And then we want to do the DFS visit, right? And then we go here. So if on when we are doing the DFS of the current node U, and then if we see an adjacent V, if the adjacent node V is white, everything is good. However, I want to add an else here. So if this the vertex V has a color something other than white, it can be black, it can be gray, and then what do we do? I want to return a true immediately, saying there is a cycle. Okay, so this is a very quick solution to find the cycles. So inside of the DFS visit, when we are visiting all the adjacent nodes to U, and then as long as we see one V, the color is not white, and then we can say, well, there is a way from U to V, that is from a white node to a gray node, or from a white node to a black node. That is, we go back to a node we have already seen before, and then that is a cycle. Okay? So, in the next part, what is the running time of the DFS? So for the DFS, we know it is the OV plus E. And what is the time complexity if we want to determine whether there's a cycle exists? And then that is OV time. So why? We have to understand, well, if we have a tree structure or a forest structure, how many edges, what is the maximum edges we can have? So for example, if we have 4 nodes, so if we have 4 nodes, Okay, and then if we want to form a tree structure, and then what? We have only three edges, or you have four nodes like this. Well, it is still only three edges. Four nodes, three edges. That is, well, if we have a tree structure with n nodes, we can have n minus 1 edges the most. Or if you want to do a forest, and then how about this is a tree, this is another tree. So in this case, we have four nodes but only two edges, right? So even though we are modifying the DFS, however, if we are visiting more than V edges, and then it will guarantee that there is a cycle. Okay, so in other words, well, the E, if we have the E higher than V plus V minus 1, and then it is guaranteed B will have a cycle, and then our algorithm will be able to detect that. So this is the reason we say, well, to detect the cycles existing in a graph, and then, well, this algorithm can be done in OV time. Okay, so that's it for today. And before I finish, there are two announcements. So the number one, homework has been extended because I found that I didn't include the video 18.3 into my playlist. So that is a very important lecture while talking about the universal hashing, and you need that to do part of the homework 5. And that, well, since for most of you guys, you didn't got the chance to see that video, and then I'm extending the homework 5 by 2 days. And another thing is, well, several of you guys have been asking me about the final exam. Well, I'm still waiting for the decision from the College of Art and Science. So as long as they give me the guideline, and then I will announce my final exam policy. And what I can assure you is, number one, and you will have enough time to work on the final exam, and it will be a take-home exam, and I'm gonna allow you either 12 or 24 hours. Okay, so you don't need to worry that you don't have enough time to finish all the questions. And number two, I'm aware that not all of you guys are in the same time zone, so, well, no matter where you are, well, you can you will have sufficient time to work on this final exam. And the final exam is supposed to take no more than 3 hours to finish. I mean, figure out your answers, and you may have to spend a little bit extra time to type your answers or to make the visualizations. And for the visualizations, I will try to make the visualizations a little bit easier for you guys, but you may need to figure out your favorite way to make the visualization. So for example, I may ask you to show me how you can do a DFS, and then you have to show me well, steps by steps, or at least the first 5 steps, for example, on doing the DFS. And then, well, you have to use Word or PowerPoint or Google Drawings to do the visualizations for the final exam. But I will make sure that making the visualizations won't take you guys a lot of time. Okay, so that's it for today, and I will see you next week. Bye.